Today, we're talking about a force that is, quite literally, everywhere, everywhere. It's the reason you're not floating out of your chair right now. It's the invisible hand that holds the moon in the night sky and keeps our whole solar system together. We're going to get a grip on the powerful, invisible pull of gravitation. So let's start with a little riddle. What on earth could a falling apple, the entire moon, and you sitting right there possibly have in common? It sounds a little strange, right? Well, the answer is the exact same invisible force. And we're going to connect all those dots. Here's our game plan. First, we'll look at the big picture with a universal force. Then we'll zoom right in on gravity on Earth. After that, we'll explore how that force creates pressure and thrust. And finally, we'll see what happens when we start talking about forces in fluids. Now, our story really kicks off with a classic tale you've probably heard: Isaac Newton and a falling apple. He watched that apple fall, and he had this absolutely brilliant idea. What if the force pulling that apple straight down is the exact same force holding the moon up in the sky? Think about it like this. Imagine you're whirling a stone on a string, round and round your head. You can feel that you're constantly pulling it in. If you let go of that string, whoosh, the stone flies off in a straight line. Newton thought, well, the moon is kind of like that stone. There must be some invisible string pulling it towards the Earth, stopping it from just flying off into the blackness of space. That center-seeking pull has a name. It's called centripetal force. For the stone, the force is the tension in the string. But for the moon, Newton argued that the force is Earth's gravity. And this is the cool part. This means the moon is basically in a constant state of falling towards the Earth. It's just moving so fast sideways that it constantly misses. And here's when Newton's idea went from brilliant to absolutely revolutionary. He realized this force isn't just about big things like planets and moons. It's universal. Every single object with mass pulls on every other object. That means you are gravitationally attracting the very device you're watching this on. Yeah, the force is incredibly tiny, but believe it or not, it's there. And it all gets boiled down into this one beautiful equation. Let's break it down. The force of gravity, F, really depends on two main things. First, the mass of the objects, the M and M. Basically, the more stuff you have, the stronger the pull. Simple. But the second part, the distance, or D, is the real kicker. See how it's squared? That means that as you move objects apart, the force of gravity doesn't just get weaker. It gets weaker really, really fast. The power of this single idea is just staggering. All of a sudden, things that seemed totally disconnected were all part of the same grand design. It's the cosmic glue that keeps our feet on the ground. It's the choreographer for the dance of the planets, and it even explains the rhythm of our ocean tides. Absolutely incredible. Okay, so we've been out in the cosmos. Let's bring this universal force right back down to Earth and see how it shapes our everyday lives. You know, when you just drop something, a ball, your keys, whatever, and the only thing really pulling on it is gravity, we've got a special name for that. We call it free fall. And during free fall, things don't just move. They speed up. They accelerate. And we call that specific rate of acceleration simply g. Right here on Earth, g is pretty much a constant, about 9.8 meters per second squared. What does that actually mean? It means for every single second something falls, its speed increases by 9.8 meters per second. But here's the part that really messes with your brain. This is true for everything, no matter how heavy it is. If you could get rid of air resistance, a feather and a bowling ball dropped from the same height would hit the ground at the exact same moment. And that brings us to something that trips a lot of people up: the difference between mass and weight. The easiest way to think about it is this. Mass is the amount of stuff you're made of. It's constant no matter where you go in the universe. Weight, on the other hand, is the force of gravity pulling on all that stuff. So, if you go to another planet, your mass is the same, but your weight, that's going to change. This chart shows it perfectly. The moon is way smaller and has less mass than Earth, so its gravitational pull is a lot weaker. If you stood on the moon, you would weigh only about 1/6 of what you do here. Look at that. That huge chunk of the circle, 5/6 of your weight, would just seem to disappear. Even though you are still the exact same you, your mass hasn't changed one bit. So, we've established that weight is a force. But, and this is a big but, the effect of that force can be totally different depending on how it's applied. Let's get into that. Here's a situation I bet you've experienced. You're walking on a sandy beach, and your feet sink in with every step. But if you lie down on that same sand, you stay right on top. Your weight is exactly the same in both cases. So what gives? The answer is all about two ideas: thrust and pressure. First, let's talk about thrust. It sounds technical, but it's really just the total force pushing straight down on a surface. So in our sand example, the thrust is simple. It's your body weight. That's it. But here is the absolute game changer. Pressure is that thrust divided by the area it's spread out over. When you stand up, all of your weight, all of that thrust, is concentrated on the tiny area of the soles of your feet. That creates really high pressure, and you sink. When you lie down, that exact same thrust is spread out over your whole body, a much bigger area. The pressure is low, and you stay on top of the sand. And once you get this, you see it being used everywhere. A nail is pointy for a reason: to concentrate the force of a hammer into a tiny spot with immense pressure. Building foundations are wide for the opposite reason: to spread out a massive weight to keep the pressure low. It's even why camels have those big, wide feet. They're nature's snowshoes for the sand. All right, for our last section, let's take these ideas of force and pressure and dive in. Literally. Let's see what happens when you put an object in a fluid and unlock the secrets of sinking and floating. So here's a little puzzle for you. Imagine you have an iron nail and a piece of cork that have the exact same mass. You drop them both into a bucket of water. The nail plummets to the bottom, but the cork bobs right on the surface. Why? We know their mass is the same, so their weight, the downward pull of gravity, is identical. There must be some other force in play here, an upward force. And there is. It's called the buoyant force, or sometimes upthrust. Anytime you put an object in a fluid, whether it's water or even air, that fluid pushes back up on it. It's the reason you feel so much lighter when you're in a swimming pool. The water is actually pushing up on you, fighting against gravity. The guy who first figured this all out over 2,000 years ago was an ancient Greek genius named Archimedes. The story goes that he had his great "Eureka! I found it!" moment when he got into his bathtub and noticed the water level rising. And this is his incredible discovery, Archimedes' principle. The upward push, that buoyant force, is exactly equal to the weight of the water the object pushes out of the way. So really, it's just a tug of war. If the object's downward weight is more than the upward buoyant force, it sinks. If the buoyant force is stronger than the weight, it floats. It's as simple as that. So let's go back and solve one last puzzle. A solid block of iron sinks like a stone, right? Its weight is way more than the tiny amount of water it displaces. But an iron ship, made of the same material, well, it's not solid. It's mostly a cleverly shaped hollow shell. That shape allows it to push aside or displace a massive amount of water. And the weight of all that water creates a huge buoyant force, big enough to hold the entire ship up. It was never about what it's made of, it's all about the shape.